Hi Gemini, we from UPM and we are from the biochemistry department. So today we are going to ask you about the multi-substrate enzyme. So my first question is, why is the ping pong mechanism called double displacement?
The ping-pong mechanism, or the double displacement mechanism, gets its name because the enzyme undergoes two distinct substitution steps during the catalytic cycle. In the first stage, the first substrate binds to the enzyme and transfers a functional group to it, forming a modified enzyme intermediate while the first product is released. Then, in the second stage, the second substrate binds, picks up that functional group from the enzyme, and leaves as the second product, returning the enzyme back to its original state. Essentially, you have a transfer of a chemical group away from the first substrate onto the enzyme, followed by a transfer of that group onto the second substrate, hence the double displacement. Would you like to know what kind of enzymes typically use this mechanism?
So for the second question, what does it mean that ping pong enzymes do not form a ternary complex?
When we say that a ping-pong enzyme does not form a ternary complex, it means that the enzyme never binds to both substrates at the same time. In a sequential mechanism, both substrates must attach to the enzyme to create a three-part complex before the reaction can take place. With the ping-pong mechanism, the first substrate binds, reacts to form the modified enzyme intermediate, and leaves the active site before the second substrate even arrives. This ensures the reactions happen in a strictly ordered fashion, with the products being released one by one. Do you want to know more about how this affects the reaction kinetics?
No thanks, but can you give me the three clear examples of ping pong enzymes, their classes, and their first product release?
Certainly. A classic example is the enzyme transaminase, which belongs to the transferase class. In its reaction, the first product released is the alpha-keto acid derived from the original amino acid. Another wonderful example is chymotrypsin, which is a hydrolase. During its mechanism, the first product released is the C-terminal peptide fragment. Lastly, you have sucrose phosphorylase, another transferase. This enzyme releases fructose first, while the glucose molecule remains bound to the enzyme to continue the cycle. Would you like to explore the specific biological roles of any of these enzymes further?
No, but next question is, how can Lineweaver-Burke plot distinguish ping pong from sequential?
The Lineweaver-Burke plot is a fantastic tool for distinguishing these two mechanisms. For a ping-pong mechanism, when you plot the data, you'll get a series of parallel lines as you vary the concentration of one substrate while holding the other constant. In contrast, for a sequential mechanism, the lines will intersect. If they intersect to the left of the y-axis, it indicates a random mechanism, whereas intersection on the y-axis points to an ordered mechanism. Does that help visualize the difference for you?
Yeah, absolutely. But my last question is, what is a limitation of using AI like you to learn enzyme mechanism? No offense.
No offense taken at all. It's important to recognize the boundaries of these tools. One major limitation is that while AI can recognize patterns and summarize information, it doesn't possess a true fundamental understanding of physics and chemistry. This means it might occasionally produce plausible-sounding but chemically incorrect details about complex reaction steps. Another challenge is the dependency on existing data. If a specific enzyme mechanism is rare or poorly studied, the AI might not have enough information to provide a highly accurate explanation. Finally, AI can't experimentally validate its findings, meaning its predictions must always be backed by empirical research to be confirmed. Is there a particular aspect of enzyme mechanisms you're hoping to learn more about using other methods?
Maybe next time. Thank you.